You're listening to Skeptoid. I'm Brian Dunning from Skeptoid.com. Why you need to care about concrete. Today we're going to point our skeptical eye at concrete, specifically at the popular figure of 8% of all greenhouse gas emissions that concrete is said to be responsible for. That's 2.8 gigatons a year as of 2020. If that number is true, then that's wildly out of control. In fact, if the global concrete industry was a country, it would be the world's third largest emitter of carbon, after only China and the United States. We humans use more concrete than any other substance, except water. And the reason is that it's great, it's inexpensive, the structures we create from it are extremely durable, and it's easy to work with, being formable into any shape. We're going to use even more of it in the future, about 1/4 more than today, as places like China, India, and Africa continue to build out their modern infrastructure. So if that 8% number is even close to true, we may have a real problem on our hands. Our first step in answering this question is to reverse engineer concrete to see what its components are, and maybe along the way see if any of them can be provided differently to keep the benefits and reduce the problems. Concrete has two basic ingredients. The first is aggregate, a mixture of fine and coarse sand and gravel, tailored to the desired properties of the finished product. And the second is Portland cement, so named because its current state-of-the-art recipe happens to physically resemble the native stone on the Isle of Portland in the English Channel. Cement consists of limestone, clay, and gypsum, combined through a special process that involves important chemical reactions. Limestone is finely ground and fed into a rotating kiln with the clay and/or sand, where it's heated to very high temperatures, up to 1,500 degrees Celsius. This produces small nodules called clinker, which are glowing red from the heat. Once they cool, they are finely ground and mixed with a small amount of gypsum. It's now what we call hydraulic cement, because it hardens upon being mixed with water to form a water-resistant solid. When it's ready to be used, about 10% of cement is mixed with about 15% water, and the rest is sand, gravel, and air to form concrete. The wet concrete is poured, and then it hardens, and this is where the chemical magic happens. The ingredients crystallize, and calcium carbonate is formed, with the interlocking crystalline structure giving its great strength. Of course, there are many variations for many specialized purposes, but this basic concrete constitutes the majority of what we use. So that's the process. Where along all that way do the CO2 emissions come from? Well, there are two pretty obvious places. The first of these, which is the biggest single contributor, is that all of those ingredients, limestone, sand, gravel, are very heavy, and they all have to be quarried. That means heavy mining equipment, a lot of trucks, a lot of tonnage, a lot of miles, and a lot of gravel crushing. All that adds up to a lot of fossil fuels getting burned. The second one is not quite so obvious, and that's the really high temperatures needed to create the clinker. We create those high temperatures by burning more fossil fuels. The next greatest source comes from the chemical processes during the heating, specifically the calcination of the limestone, converting it from calcium carbonate to calcium oxide. For every ton of raw materials that goes into the kiln, about 600 kilograms of CO2 is created. And the next largest source is power generation to run all of these things. And you know the process has to be pretty bad when power generation is only the fourth largest emitter. Take it all into account, and considering the incredible size and scope of the worldwide construction industry, and suddenly that 8% looks like a much more realistic and sobering number. Combined with the projected steep growth in concrete production over the coming decades, and we have a very clear answer to our basic question today, which is yes, we all do need to care very much about concrete. And as always, it's important to note that these are all hard numbers from direct measurements. There are no estimates, guesses, models, or pundit spins going into this 8%. It's not a thing that's in any meaningful dispute. With 8%, projected to rise, being such a large number, it's tempting to look at concrete as low-hanging fruit in the fight against climate change. The fact is, we're not going to stop using it, or reduce our use of it, just like we're not going to stop driving cars. The pursuit of unicorn solutions is a fool's errand. But that doesn't mean concrete can't still be low-hanging fruit. It's just that reduction of its use is not going to be the way we improve on that 8%. I'm an efficiency nerd, and I encourage everyone else to be one too. Efficiency is nifty. Efficiency is all about doing more with less. Consumers want more of things, I certainly do, and industry wants to provide that using less resources. Efficiency is a win-win. True efficiency means everyone gets to meet their own self-interest-driven goals, while the overall system benefits from the public interest goal of lower environmental impact. When we apply this to concrete, it means we want to find a way to produce more or better concrete for a lower carbon cost. With the right incentive structures in place, a lower carbon cost means a lower money cost. Can that be done? Well, this is where we say, yay, science. In 2021, the Global Cement and Concrete Association partnered with the World Economic Forum to establish an initiative called CAC, Concrete Action for Climate. Its goal is to make all concrete carbon neutral by 2050. It seems a monumental target. 2050 is not that far away, and 8% of all CO2 emissions in the world is a very big slice of the pie. However, the good news is that the industry is already well underway. Since 1990, industry has managed to reduce carbon emissions per ton of concrete produced by 20%, even though total emissions since then has increased, since production, driven by China's explosive infrastructure growth, has tripled in that same time period, making those reductions so far enormously impactful. The first way that emissions have been reduced is that a lot of the kilns have been replaced with more energy-efficient designs. This is ongoing. There's still room for a lot of progress, as there are still lots of inefficient kilns out there. The second thing that's been done is to use more non-fossil alternative fuels in processes throughout the production cycle, including heating the kilns. This remains an active area of innovation. Third, and finally, there's been a lot more emphasis on using different kinds of concrete for different applications. There are a number of variables we can play with when formulating concrete: strength, weight, durability, color, flexibility, thermal properties, etc. For applications in which trade-offs are acceptable, concrete formulations can be used which require less clinker, replacing it with materials such as waste from coal combustion and steel making. This usually ends up costing less as well, so it's a win for everyone. This tweak of using less clinker, whenever it makes sense, means the whole industry has been producing proportionally less clinker per ton overall. Just since 1990, the overall amount of clinker in the cement component of concrete has been reduced from 90% to 65%, and the CAC targets getting that down to 60% by 2050. They may even beat it. So those are 3 effective ways we've been able to reduce the carbon cost of concrete in the past. Are those alone enough to get us to net zero by 2050? The answer to that is probably not. It's a no according to today's knowledge, but you never know what crazy new innovations might boost any of the 3. We will need a 4th lever. That 4th way to reduce carbon from concrete is something that exists today only in the experimental phase. It's called simply innovative technologies, and it includes all kinds of different ideas that researchers are tinkering with. This involves everything from carbon capturing and sequestering it within the concrete, to novel ways to electrochemically calcinate the limestone, to new ways to recycle used concrete. Concrete can only be recycled into aggregate, but can't be used in the production of clinker, due to the chemical changes it has undergone. A number of companies are already working toward commercializing the sequestration of carbon into concrete, which has come to be called reverse calcination. This can be done as late in the process as at the job site, where ready-mixed concrete can be directly injected with CO2. The CO2 promotes some of the same chemical reactions in the concrete as does the water, so it not only works well, it can also literally create new limestone within the concrete, making it harder and stronger, a better material. Limestone is one of the best ways to permanently sequester CO2. The Earth's limestone is already its biggest carbon sink. It's a biological sedimentary rock formed mostly from the shells of prehistoric sea creatures. Recall one of the reasons Earth is a nice place compared to Venus, which is a scorching hell caused by runaway greenhouse effect. Life developed on Earth, and thus sequestered much of our carbon into limestone. Venus never had life, so its carbon dioxide became its atmosphere, resulting in billions of years of global warming. Other researchers are working on electrochemical calcination. Chemically, it can be devilishly complicated, but it can provide complete capture of the carbon released by the calcinating limestone, plus oxygen and hydrogen to make enough oxyhydrogen gas to burn and provide all the heating that's needed, with zero carbon emissions. Now, there's one other challenge that our growing need for concrete has given us that has nothing to do with carbon emissions: the global sand shortage. We need the sand to make the concrete, and sand mining has reached a critical point in many parts of the world. So that's a very real issue, but it's beyond the scope of today's episode. I'll probably tackle it in a future show. We're not ignoring it today, we're just focusing on the carbon cost of concrete as today's topic. Concrete is an awesome thing that we love. Freshwater infrastructure, increasingly being installed for the first time in many parts of the world and upgraded in others, is made of concrete. Hospitals are made of concrete. Fusion reactors, if we ever get to them, and the Generation 4 nuclear reactors we'll build in the interim, will all be made of concrete. Concrete is essential to our carbon-neutral and freshwater future. Thus, the innovative technologies and other ways we develop to reduce its carbon footprint are also essential. They are exciting areas of research, and they're all growth industries. So, care about concrete. Next time you walk past a concrete wall or pillar, slap it 5. It's your friend. Your long-term friend. This episode is dedicated to the memory of a great friend of the show, a major Skeptoid supporter for more than 12 years, Dan Murphy. But much more than that, Dan was a brilliant mind, and I was one of the many lucky enough to have him in my life as a friend. Rest in peace, Dan, and thanks for everything. Skeptoid will always carry your mark. A great big Skeptoid shout-out to Skeptoid Premium members Matt Go Primo, Aaron the Puppy Dentist forsayeth, Eric Woods of Cheyenne for saving the cloud, and Mark McCady. Are you an educator? Have you seen our Teacher's Toolkit? It's a way to share all the best Skeptoid episodes with your classroom in a secure, organized, and controlled way. Come and check out our 3-minute video explainer to see how it works at skeptoid.com/teachers. And pick up an autographed Skeptoid book or a t-shirt in our online store. We've got all the styles, sizes, and colors at skeptoid.com/store. You're listening to Skeptoid, a listener-supported program. I'm Brian Dunning from Skeptoid.com.